Question B3 from the 2012 Advanced Higher Applied Maths, a 6-mark question on matrices. Fairly straightforward looking at it, it's just like multiplying and adding matrices. But of course they can be quite tedious in the amount of calculation, but you notice this matrix is particularly empty looking, which should simplify matters a lot. So what's the first thing? Calculate m squared for 2 marks. Notice that doesn't just mean square all the little bits. I'll have to write it out. So that'll be 100,310,00 lambda times 100,310,00 lambda. Now, when they're particularly empty like this, especially if there's only like one entry in each of those rows, it's not so bad if there's just 2 as well, then you can answer this multiplication a slightly quicker way than going through the standard scalar product of the row vector times the column vector. I'll start it off that way though. So that means you've got multiplying them in order, scalar product. 1 plus 0 plus 0 is 1. Nothing plus nothing plus nothing is nothing. Or maybe I'll say 0. 0 plus 0 plus 0 is 0. But I could have got that a much quicker way. Next row. 3 plus 3 plus 0 is 6. 0 plus 1 plus 0 is 1. 0 plus 0 plus 0 is 0. And the last one. 0 plus 0 plus 0 is 0. 0 plus 0 plus 0 is 0. 0 plus 0 plus lambda squared. So that would be the answer for 2 marks. That was using, if you like, the proper multiplication, row times column, scalar product multiplication. However, when they're particularly empty, when you've got a sparsely populated matrix, or I like to say a little desolate matrix, this isn't quite as desolate as it could be, then you can interpret it a different way. You can think of this first row here as an instruction of what to do with the rows here to produce the first row in the answer. So this one says, take one of the first row and none of the other 2. So I'll keep the first row and that's all, 1, 0, 0. This instruction says, I'll have 3 of the top row, 1 of the next one, and that's all. So I'll have 3 of them and 1 of them. That'll be a 3 onto that, making it a 6, 1, 0. And this one says I'll have none of the top row, none of the middle row, but lambda times the bottom row. So lambda times the bottom row gives me that. It's just a slightly quicker multiplication when it's sparsely populated. Just thinking in terms of that's an instruction for what to do with the rows. Remember, those numbers have to match the row numbers down here. 1 of the top, none of the next one, none of the next one, and you can do them all at once if it's sparsely populated, because there won't be much arithmetic to do. Anyway, that was the first 2 marks. B. Now calculate m plus m squared plus m cubed. Oh, well, you've got 2 ways you could do this. You could then find m cubed by multiplying this by m and then add all 3 together. We'll do that first. So I'll work out m cubed. Well, that will be 100,310,00 lambda times 100,610,00 lambda squared. And I think I'll just do it the other way. Just the top row, 3 of the next row, 3 of the top row and 1 of them, so that'll be a 3 onto that, and that makes it a 9, 1, 0, and that just says lambda times, none of the top, just lambda times the bottom one, 0, 0 lambda cubed. That would be a mark. And then add them all together. Oh. So that means you've got 100,310, easy enough marks, but very tedious, isn't it? 100,610, do I need to write them out? I don't know. And 100,910,00 lambda cubed. So that all together, the answer would be, top row, 300, 18, 30, and that's just going to be 0, 0, and I wish I left myself a wee bit more space. Boing, there we go, because it's going to be lambda cubed plus lambda squared plus lambda. Nothing really to it. There's another 2 marks. Of course, an alternative would have been to take m out. Still got to do a multiplication, I've still got to do an addition. Take m out, remember that leaves an I, not a 1. I plus m squared. So that would be m multiplying, and m was 1, 0, 0, 3, 1, 0, 0, 0 lambda, times adding up what you've got so far. Would you be allowed just to jump in with that? Or would I have to show the parts? Because I is just going to add 1 onto the main diagonal. So I'm just adding these 2 here. Maybe I'll just put it to the side here. 1, 0, 0, 3, 1, 0, 0, 0 lambda, plus 1, 0, 0, 6, 1, 0, 0, 0 lambda squared, and of course I at the beginning, 1, 0, 0, 0, 1, 0, 0, 0, 1. So that altogether top row is going to be 3, 0, 0. Next row is going to be 9, 3, 0. Bottom row is just going to be 0, 0, and then I've got a 1 plus lambda squared. Then multiplying, that says I'll just have the top row. Right, there you go. This says I'll have 3 of the top. Well, that'll be a 9, and then add on this. So that's an 18. 3, 0, and this says just multiply the bottom by lambda. 0, 0, and then that'll be lambda squared, lambda cubed, as before. It isn't easy enough 2 marks, but it is very tedious. It does take a lot of time. You've got to work for your 2 marks, time-wise. Now part C, for what values of lambda does m have an inverse? Well, it'll have an inverse as long as the determinant isn't equal to 0. So what is the determinant of m? Well, luckily the top row is just 1, 0, 0. So it'll just be 1 times its minor, the 1, 0, 0 lambda, because the rest will just be zeros. Could put that in, minus 0, plus 0 if you like. And that's just lambda minus nothing, so it's just lambda. The determinant of that matrix is lambda. So, when has it got an inverse? Do I have to write that down now? So, has an inverse when, as long as it's got some number here, so when lambda is not equal to 0. So it was 1 for getting the determinant, and 1 for knowing that the determinant can't be 0 if you want it to have an inverse.